Hello everybody, Mr. Hasty here again. Today we're going to be talking about Chapter 12. Chapter 12 is on the different states of matter. And we've already discussed this earlier in the year, but now that we understand more, we're going to take a more in-depth look at the states of matter, starting with gases. So kinetic molecular theory is a theory developed in 1860 by Ludwig Boltzmann and James Maxwell. And what it says is that the properties of matter, a lot of the physical properties of matter, are determined by the motion of their particles. So, where we're going to talk about this is in different states of matter. So, we've talked about this. All matter is moving. All matter is in motion. Even things that are in solid, their atoms are wiggling around. So what a solid actually is it's a fixed arrangement where the molecules are all combined and close together. But those molecules are moving. They just can't move enough to get out of position. So an easy way to think about this is imagine being in a tightly packed group of people. You can move around, you can move yourself around, but you can't get out of position. You're stuck in your position. Now, once those particles start to move around a bit more, but they stay relatively connected, there's still forces of attraction, that's where we get liquids. Liquids are particles that are still attracted, they're still in contact, they still want to be in contact and touch each other. However, they are not in a fixed position. They can move around a little bit more. So if we know what happens when we heat a solid up enough, it turns into a liquid. And if we think about that, what that's essentially meaning is that the particles are moving around enough that they're actually breaking formation and starting to move around each other. And then finally, we know if we heat up liquids, we eat gases. Now, what a gas is, we're going to assume we have a lid on this guy, on this container, so we'll make there be a lid. Basically, the forces that are holding them together stop holding them together, and you have particles just bouncing around in there, just flying all around inside. And a lot of that is not actually space taken up by particles, it's space taken up by empty space in between them. The area between the particles is empty space. So what we're going to do now is we're going to move into talking more specifically about the properties of gases. We'll get into the properties of liquids and solids a little bit later. So a few things we need to know about gas particles. Number one, gas particles are small, and there's empty space between them. That empty space is important for understanding why they're allowed to move the way they do. They also are not attracted to one another. There's not enough attractive force to keep them held together. So when we talk about them, we're going to talk about the amount of energy these particles have. They are always in motion, and the amount of energy in motion called kinetic energy that a particle has, and we're not going to use this formula, I just want to have this formula around to talk about. The amount of kinetic energy something has is equal to 1/2 of its mass times the velocity squared. So velocity gets squared, so it's a big deal. Now, the particles are going to bump into each other. They're going to bump into the container. If we're looking at this guy right here, they're going to bump into the glass. They're going to bump into the top, bottom. They're going to bump into each other. They're going to have collisions. And we call these collisions elastic. An elastic collision is a collision where no energy is lost. Now, we haven't talked too much about energy in this regard yet. But basically, what we have to understand is all the energy is transferred somewhere. Now, what temperature is? Well, if we look at individual particles, some of them might have a lot of energy, some of them might have not so much. So what temperature is it's a measurement of the average kinetic energy of a substance. So we're going to go back and talk about our kinetic molecular theory model in regards to that. So if we look at this, solid, they're moving, but they're not moving very much. As we heat them up, the movement increases to a point where they can kind of move around each other. And then if the temperature increases even more, they break free and they're just moving around on their own free will. Another thing that this allows us to do is gases are what we call compressible. Because of all that empty space between them, we can change the volume of the gas without actually changing the amount of the gas. So if we make the volume smaller, that's called compression. And if you look, we have the same number of particles, they're just bouncing around in a much smaller space. If we expand them, called expansion, then we have the same number of particles bouncing around a much bigger space. And these concepts are going to relate to the volume, is going to relate to the pressure, is going to relate to the temperature, the movement of those molecules. We're going to talk about that in more detail later. Next thing we're going to talk about are the concepts of diffusion and effusion. So they're used rather synonymously. We're going to define diffusion. Diffusion is the movement of one material through another. So we can understand diffusion as number one, the movement of gas particles. When someone cooks food in the house, that creates gas particles that to us smell good. And basically, the gas particles move from areas of high concentration in the kitchen where there's a lot of them, and they diffuse throughout the house. They move throughout the house, and that's how you can smell something being cooked in another room. Another example is if you have a glass of water and you were to put food coloring in it, you can see that food coloring spread out through the water, and we call that diffusion as well. Now, the term effusion is the passing of a substance through a small hole. So if you've ever taken a bucket of water, for instance, and poked a hole in the bottom of it, let the water come out, that is effusion. Now, Graham is a scientist who was studying the rate at which things effuse. And he found out that the rate of effusion is inversely proportional to the square root of the molar mass. Now, we're going to have a formula that goes along with this. But what that means is how fast something escapes. And he did this work in a vacuum, but it can also be applied to roughly approximate for like gases moving around. Basically, if you release a gas into an area, how fast does it move through the area? And what he found is it's inversely proportional to the square root of the molar mass. So we're going to use this comparatively between two substances. So when we talk about the rate, we're talking about how many moles per minute or how many moles per second. So what we're going to have for a formula here is the rate of gas A over the rate of gas B is equal to the square root of the molar mass of B over molar mass of A. And one thing I would like to note is that a lot of people think this is going to be a mistake because my A is on top and A is on bottom, and when you normally work with proportions, you make sure if A is on top on the left, A is on top of the right. Well, it's inversely proportional. So that means they should be opposite of each other. The other thing I'd like to note is there's a square root over both of them, but you could easily have done it as the square root of the top one divided by the square root of the bottom one so that you had two separate square roots. Either one of those is acceptable. So let's see these in action here. Example 1. Ammonia has a molar mass of 17.0 grams per mole. Hydrogen chloride has a molar mass of 36.5 grams per mole. What is the ratio, that's important, of their diffusion rates? So when we look at our formula says rate of A over rate of B equals square root of molar mass molar mass B over molar mass of A. So what it's asking for is the ratio. It wants us to find this right here. So that means we just need to do this part. So in this case, I have the square root, the molar mass of B. Well, the molar mass of B, the second one listed here was hydrogen chloride, 36.5. And molar mass of A would be 17.0. And we grab our calculator, we do that to 3 sig figs, we get 1.47. And we would not have units here because it's a ratio. So ratios are often unitless. So what does that mean? It means that A, which A was the ammonia, basically moves 1.5 times as fast as hydrogen chloride. So if we were to release both these gases simultaneously, the hydrogen chloride would reach a certain point in the room 1.5 times faster than the ammonia would reach it 1.5 times faster than the hydrogen chloride. All right. So oxygen gas is mixed with argon, and when we say argon, the noble gases are always just single atoms. They're not like Ar2. Like oxygen gas will be O2, but argon will just be Ar. If the argon is effusing at a rate of 2.8 moles per minute, how fast is the oxygen gas effusing? So we're looking for one of the rates here. So we're going to call that the rate of O2 is what we're looking for. And we would need the rate on bottom would be the rate of argon, 2.8 moles per minute. Square root. So on the top of this, we're going to have the molar mass of argon. Remember, if the rate of argon is on bottom, the molar mass is on top. So we would just go under our periodic table and look up how much one argon atom is going to be in terms of mass. And we get 39.948. And that would be grams per mole, but we don't need our units here. And then on bottom, we have the molar mass of oxygen. Remember, oxygen is O2, so we need 2 oxygen atoms. It's going to be 31.998. Now, how do you solve something like this? We do the entire right side on our calculator, and then we're going to end up multiplying it by 2.8 to get rid of that 2.8 on the other side. So for our rate of oxygen gas, it's going to equal the square root of all that then we're going to have to multiply that by 2.8 to get it off the other side. So we do that calculation, we get 3.1. Now what would our units be? We're looking for a rate of O2, and our rate of argon was given in moles per minute, so our rate of oxygen is going to be in moles per minute. And this kind of stands to reason. Oxygen is slightly lighter, which means it ends up moving slightly faster. These types of problems are a little tricky, but I think they're probably some of the trickier math that we have to do in this chapter. So if you're good with this stuff, it's going to be pretty easy. All right, guys. See you next time.